everyone, welcome to InsightsByRish. In today's video, I am going to implement a project of credit card fraud detection using artificial neural network. And for that, I am going to make use of this particular dataset from Kaggle of credit card transactions fraud detection dataset. Now, if you want to know more about any particular column, the description of every column is also available here. So I will provide the link of this dataset in the description box. Do check that. Now going back to the code, I am going to make use of Google Colab IDE for this particular project, and I have already downloaded the dataset and I have also uploaded the dataset in the Google Colab environment. As you can see here, I have already uploaded that CSV file here. Then also before beginning with the project, let me also inform you that you have to change your runtime type. Go to runtime and change the runtime type to T4 GPU. By default it's on CPU, but you have to change it on T4 GPU, because if you continue on CPU then it might become very slow, and hence go to T4 GPU and do that before beginning with project, because if you do that later then you have to rerun all the cells again. Now we'll begin with the project. First we will import pandas here. We'll say import pandas as PD. Let's run that. And now we will load our dataset in a variable called df. Let us say pd.readCSV. Here we have to provide the path of our dataset. Now I have already uploaded the dataset here, so I will just copy the path from here and I will paste it here. Let's run that. And now we will check the shape of our dataset. So as you can see, we are having this many rows in our dataset and 23 columns. So if you want, you can also display the dataset, the first 3 rows. And this is our dataset. It consists of 23 columns, and you can just click on this particular icon to make the table more interactive. The next thing that we have to do here after displaying the table is we have to delete the unwanted columns. There are many unwanted columns here, and to do so, first you will display the names of all the columns. So we'll say df.columns. Let's run that. And these are all the available columns. Now you just have to keep the columns that are required, and you have to delete all the unwanted columns. So the first step here is dropping the columns. Actually unwanted columns. Then here you will say df.drop, then columns, and here you have to provide the list of all columns that you want to drop. So the first column here, if you take the look at your dataset, is unnamed 0. You don't require this column for any kind of prediction, so you will provide that. I will just copy the name from here. The next column here is the transaction date and the transaction time. We also don't require that. Then after that, the next column is cc_num. After that, the next column that we have is merchant. Then this is the name of merchant. Again, we don't require that, so I will also say here merchant. After the column merchant, the next column that we have is category. Now category is the column that we require, so we are keeping that. After that, the next column is AMT, and if you want to know what is AMT, then go back to the Kaggle and check for the description. So AMT is the amount of transaction. Now we have to keep the AMT. That's an important feature as well. The next columns are first and last. That is the first name of the credit card holder and the last name of the credit card holder. So we don't require that column, and hence I will say here first and last. After that, the next column here is gender, is what we require. Then we don't require the street and city columns. We will keep the column state here because that's a more generalized one. We don't have a lot of states, but if you check for the unique values from street and city, there will be a lot of unique values, so it will be a kind of unwanted data, and hence we will delete the street and city column, but we will keep the state. So let me also write here street and city. After that, as we are keeping state, the next column is zip code. Also, we don't require this zip code, so I will say zip. Then after zip code, the next column is latitude and longitude, and then the city population. Now city population is what we require, and hence we will keep this column of city population, but we will delete the latitude and longitude column as we don't require that. I will say here latitude and longitude. Then after latitude and longitude, the next column here is city population, that is what we are keeping. Next is job. Now job is again the column that we are going to keep because it consists of all the categories of job that the credit card holder does. So we are keeping that. The next column is DOB, that is the date of birth, and we don't require that. So I will also say here DOB. Let me bring it on new line. After DOB, the next column is transaction number. Now transaction number is again a very unwanted column because every credit card holder will have a different transaction number, so we can't make any actually predictions based upon that. I will say here transaction number. After that, the next column is Unix underscore time. We also don't require that. Let's delete that. And after that, the next column is latitude of merchant and longitude of merchant. Again, that's a very useless column, so we will delete that as well. And then the merchant longitude. And the last column, that is the eastport column, is our target feature. So that's a very important one. So these are all the columns. This is a list of columns that you have to drop. And here I will provide one more attribute here of in place is equal to true in order to make this changes permanent. Let's run that. So okay, it's Unix. It's somewhere here. Fine. Now we will again display the data set. As you can see, now this is the data set that we have. We have the category, the amount of transaction, gender, state, city population, job category, and whether it's fraud or not. 0 means it isn't and 1 means it is. Now after that, we will check for null values. So the second task that we are going to do here is checking for null values. So let me write here checking for null values. So I will say df.isNA.sum. It will give me the count of null values from every column. As you can see, we have just a single null value in every column, and hence we are going to make use of drop NA method. That is, we are going to drop the rows which consist of null values, because there is just a single row that consists of null values. So even after dropping a single row, there won't be much loss of data. So we will say df.dropNA, and then in place is equal to true in order to make the changes permanent. Let's run that, and let us now check for null values here. As you can see, every null value is deleted now. Now we don't have any kind of null value. So we have removed the null values, and after that, the third task that we have to do here is, let's say third task. Now when you take the look at your data set, you can see that you have some categorical values here, like the column category, gender, state, and job. These are all the categorical values. And in order to train the machine learning model, you need to convert these categorical values into numeric ones. The first column that we are going to convert here is category. So the third task here is converting categorical values to numerical. Fine. And we have to decide which method we have to use for this particular purpose. We have various methods here: one-hot encoding, label encoding, then replace method, map method. There are various methods. So we are going to decide that depending upon how many unique values we have in that column. So let me say here df category dot unique. Let's run that, and there are many unique values here. So we are going to make use of one-hot encoder here, and from that we are going to make use of getDummies function. So what we are going to do, we are going to create a new data frame here of category underscore df, and here we will say pd.getDummies. And here we have to pass the column for which we have to get the dummy values, that is in the combination of ones and zeros. So the column name is category. Let's run that, and let us display the category underscore df. As you can see, right now the values are in the Boolean form, that is true and false. This is because we have to explicitly convert this into the integer. So let's do that. Let us say as type int. Let's run that. And now, as you can see, now the values are in the combination of zeros and ones. This is what we wanted. So we created a separate data frame for category, and there we mentioned all the names of categories that were available, all the unique values of categories that were available basically. And then we presented the values in the form of zeros and ones. That is, in the first row, if you see, the value 1 is present for MISC_net, which means this particular row consists of this category. Fine. So this is how basically you interpret this. Now what we have to do, as we have converted the categorical values from category column to numeric ones, we can delete the original category column, that is this column, from the df data frame. So we'll just say df.drop columns is equal to category and say in place is equal to true in order to make the changes permanent. Let's run that. And you can even verify that by displaying the data frame. So now you don't have that category column. The next task is, now that we have this two different data frames, two individual data frames. The first is df, that consists of all the data, and then the particular data frame for category. We have to concatenate both of this. So we will say df. Now this is a new data frame with the same name df, and we will say pd.concat. Here we have to provide the names of the data frames that we want to concatenate. The first data frame is df. This data frame is the new data frame with the same name, and this data frame is the previous one. Fine. So we'll say df, and the next data frame is category_df, that is this one. And we are concatenating on the basis of columns, hence we will say access is equal to 1. Let's run that. And let us now display the data frame. As you can see, now we have that zeros and ones combination of category column here in the form of numeric integer value. Fine. So this was the conversion of one column from categorical to numerical. We have several more similar columns here. The next column here is gender. So again, we will check the unique values from gender column. We will say gender dot unique. This is just to identify which method we have to use. So as you can see, we just have two unique values here, female and male, and hence we are not going to use one hot encoding here, but we are going to make the use of replace method. So let us say df gender dot replace, and in replace what we are going to do, we are going to say wherever we encounter the value female, we are going to replace that with, like, wherever we are going to encounter the value f for female, we are going to replace it with the value 1, and wherever we are going to encounter the value male, that is m, we are going to replace it with 0, and just say in place is equal to true. Let's run that. And now when you check the unique value from the gender column, now you can see the values are in the form of ones and zeros. Fine. So we have also converted the categorical value to numeric one from the column gender. The next column here is state. Now first we will check the unique values from state column here. So let me write here df state dot unique. Let's run that. And there are multiple states here. There are many values of state available here. That is, many unique values of state actually available here. And hence we are again going to make use of one hot encoding. So we will again create a new data frame of state_df, which will consist of values for state_df in the form of zeros and ones. And here we will say pd.get_dummies, then the column for which you have to generate the dummy values, that is the column state. And then we have to also say as type is equal to int to explicitly convert the data type into integer. Let's run that. And let me display this data frame. As you can see, these are all the names of state and they are represented now in the form of zeros and ones. Fine. So this is what we were supposed to do. Now again we will delete the original state underscore df column from the df data frame. This original column, we don't require it anymore because we have already generated the dummy values for this column. So we will say df dot drop columns is equal to state and just say in place is equal to true. Let's run that, and if you want to confirm you can just say df dot head. So as you can see, now we don't have that state column anymore. But the next task is to concatenate this state underscore data frame with the original df data frame. So to do that, again we will create a new data frame with the same name df. Now this df is a new data frame with the same name df. And here I will say pd.concat. Here I will provide the name of data frames that I have to concatenate, and the first data frame is df. Now this df is the previous data frame df, and this df is the new one. Then I will say df and then the state underscore df, that is this data frame. Fine. Now here again we are going to concatenate it on the basis of columns, and hence I will say axis is equal to 1. Let's run that and let us display the data frame here. So as you can see, now we have in total 69 columns into this dataset. As you can see, now we have 69 columns into this dataset after concatenating the state underscore df in the original data frame. Now the last column for which we have to perform conversion here is the job column. And if you check for unique values here, just say df dot job dot unique. Let's run that. And as you can see, there are a lot of unique values for job column. So there are a lot. If you want to check the count of unique values for the job, you can just say here shape. Let's run that. As you can see, you have in total 475 unique values in the job column. So if you generate the numeric values for job column in the similar pattern, that is in the combination of zeros and ones, then you will add 475 more columns into this df dataset. So we will again use the get dummies function here. I will say df is equal to pd dot get dummies. Actually, before this, we have to create a new data frame of job underscore df, and here we will say pd dot get dummies. And here we will pass the column name job. Then explicitly convert it into integer, so as type int. Run that and display the job underscore df. As you can see, we have in total 475 columns into this data frame, and we are going to concatenate this data frame with the previous data frame df. But before doing that, we will delete the original job column from this data frame as we don't require it anymore. So we'll just say df dot drop columns is equal to job and in place is equal to true. Let's run that, and after dropping that column, now we have to concatenate this job underscore df with the previous data frame df. So we'll again create a new data frame with the same name df and then pd.concat. Here I will provide the names of data frame that I have to concat, which is df and job underscore df. Then again we are concatenating it on the basis of columns, and hence I will say axis is equal to 1. Let's run that and let us display actually the shape of our data frame, the dimension of the data frame. As you can see, now we have 543 columns in total and 19,475 rows. So if you want, you can even display the dataset, although it will abstract some columns here. So these are all the columns. Now as you can see here, we don't have any categorical column anymore. So we are done with this. So the next task now, that is the fourth task, is to divide our dataset df into two parts. The first part will consist of input data frame, that will basically consist of all input columns, and the next part, that is the second part, will consist of a variable y which will store our target values. We'll say dividing the dataset. So we will say variable x, which will be of type data frame. It will store all the columns, like the 543, all the columns available here, except for the column isFraud. This isFraud is our target feature, and this is what we don't have to include in our input data frame. So we will just make the use of drop method here. We will say df.drop columns is equal to is_fraud. Why we are doing this? Because we have to include every column from the df data frame in this x data frame, except for the column isFraud, because this is our target feature. And in a variable of y of type series, we will include the target variable or the target feature, that is isFraud. Let's run that and let's display the input data frame here, that is x. So as you can see, now this data frame consists of 542 columns, that is one less than the previous, and that one less column, that is the isFraud column, now is present in y variable. Now the next thing that we have to do here after dividing this successfully is, if you check the value counts here, that is, let me display the value counts first. Value counts basically means the count of rows that belongs to every category. So here we have two categories, the category 0 and 1. 0 means it is in fraud, and 1 means it is fraud. So as you can see, there are more rows for the first category, that is the category 0, but very less number of rows compared to the first category present for the category 1. And this is what represents imbalanced dataset. So working on an imbalanced dataset is never a good idea. Hence we have to handle this imbalanced dataset. And to handle the imbalanced dataset, we are going to make use of smooth technique. So the next task here, that is the fifth task, is handling the imbalanced dataset using smooth technique. So smooth basically stands for synthetic minority oversampling technique. Here what we do, here we oversample, synthetically oversample the minority class. The minority class means here the minority class is category 1, that is isFraud category, which is the minority class, that is it just consists of 132 samples, which are very less compared to the category 0. So this is the minority class, and we are going to oversample the instances of this particular class here. Let us say from IMB learn dot oversampling, we are going to import smooth, and then we will create an object of smooth here, that is smooth. Here there is a difference. This smooth is in lowercase and this smooth is in uppercase, so this is kind of case sensitive. So this both things are different. This smooth is a module and this smooth is an object of that module. So we'll say smooth. Then the sampling strategy. So sampling underscore strategy. Now what is the sampling strategy here? That is what you have to sample, the minority class or the majority class. In this case we have to sample, that is we have to produce more synthetic samples for the minority class, and hence the sampling strategy here is minority. And then you will again say x comma y, that is with the same name. If you want, you can even give the different names here, but I will keep the names as it is. X is your input data frame and y is your target feature. So you will say smooth, that is the object of smooth module, dot fit underscore resample, and here you will again provide the x and y. Now this x and y are the new data frame names, that is x is the new input data frame after performing smooth, and y is a new target variable after performing smooth, and this x and y are the previous ones. Fine, let's run that. And now you can again check the value counts in the y variable. So let's check the value counts again. As you can see, now we have equal number of samples for both the categories. Initially we had very less number of samples for the category 1, but now we have equal number of samples for both the categories, and this is a kind of balanced dataset that we have to work upon. So after balancing the dataset, now when you check the shape of x here, so now you will have double the rows than the previous. So initially you had some 19,475 rows in your data frame, but now you have 38,686 rows as you have generated more synthetic samples for the category 1. After balancing the data set, the next task that you have to do, that is the sixth task, is data normalization. And what we mean by that is, if you say x, that is your input data frame dot describe, let's display that. And when you check the minimum value and the maximum value for every column, you can see that every column is on a different scale. That is, the minimum value and the maximum value is different for every column. So the data normalization task is performed to bring all these columns onto one single common scale. And we have various data normalization techniques here, but we are going to make use of a min-max scaler, which will basically transfer all the values from every column between the range of 0 to 1. That is, every column will have the minimum value 0 and the maximum value 1. So we will say from sklearn.preprocessing, we will import the min-max scaler. And here we will create an object of min-max scaler module, which is scaler is equal to min-max scaler. After that, we will say x square bracket colon is equal to scaler dot fit underscore transform. Now these are the two methods, the fit method and the transform method. I am doing both the things in one single go. If you want, you can do both the things in two different parts. So transform, and here I will transform my x data frame. Now as you can see, this x is the previous input data frame, that is this one, and this x is the name of our new data frame. Now the reason behind providing this square bracket and colon is, if you don't provide this, then the transformed values will be stored in the form of array and not in the form of data frame. But we want our transformed values to be stored in the form of data frame and not arrays, and hence we have provided this. Let's run that. And now let's display the dataset, that is the input dataset again. Now when you check, you can see every value is between the range of 0 to 1. So no value is greater than 1 or lower than 0. So this is what data normalization does. Now after this, after performing data normalization, we are done with every kind of pre-processing step in our dataset. Now we have to divide our dataset into the training set and testing set. So the next task here, that is the seventh task, is train test split. Now I have already explained about various train test split methods in my previous video. I will provide the link of that in the description. If you want, you can check that. So here I am going to use the holdout method of train test split. So from sklearn.model selection, I will import train test split module here. Then here I will say x underscore train and x underscore test, then y underscore train and y underscore test is equal to train test split. And here I will provide the input data frame, that is x, and the target feature, which is y. Then the test size, you can give any test size as you want. I will say 0.2, that is 80% data in the training set and 20% data in the testing set. And then random state is equal to 42. And I will also say stratify is equal to y, that is I want equal number of samples of every category in the training and testing set. So let's run that. And now you can check the shape of xtrain dot shape and xtest dot shape. So out of initially we had 38,686 rows. Out of that, now 30,948 rows are in the training set and 7,738 rows are in the testing set. Even if you check the ytrain dot shape here, actually value counts. You can see you are having equal number of samples for both the categories in the training set, and even in the testing set you can see ytest dot value counts. You can see even in the y-test you have equal number of samples for both the categories, and this is because we have provided this attribute stratify is equal to y. If you don't provide this attribute here, let me just remove that and we'll again rerun this. Now you can see we are having different number of samples for every category here. In the training set as well and in the testing set as well. So it depends upon you whether you have to provide that stratify argument or not. It's completely an individual matter. It won't affect much, but still I will provide it. Stratify is equal to 5. Let's run that. So now we are done with train test split and we have did everything. Now we will actually start our main task, that is of building the model. So now we will start our next task here, that is our 8th task, which is building the artificial neural network. So here first we will import the necessary libraries, that is import TensorFlow, STF, and then from TensorFlow import keras. So after importing the libraries, now we will say model is equal to keras.sequential. So we are building the sequential module here. Sequential. So here we will provide the dense layers. The first layer will be our input layer, and also it will have our hidden neurons, that is hidden layer 1. So we will say keras dot layers dot dense. Now here we have to provide the value that how many neurons we want in our first hidden layer. If you check that we have in total 542 columns. Fine. So that is we will have the 542 neurons in our input layer. Now in our first hidden layer we can have few less neurons. So let us say that we want 300 neurons in our first hidden layer. So 300. Then the input shape is 542. And then the activation function. Now the activation function for the hidden layers is always ReLU, irrespective of whether it is a binary classification model or a multi-class classification model. So this was the input layer as well as the first hidden layer. Now the next will be our hidden layer 2. Choice of hidden layers depends completely upon you. As many hidden layers as you want to add, you can add. The next hidden layer will say keras.layers.dense. Now again we have to provide here the value of neurons in our second hidden layer. So let us say half of the neurons as compared to hidden layer 1, that is 150 neurons in our second hidden layers. And now we don't require to provide the input shape anymore, it's just required in the first step itself. So here we require activation. So activation is equal to ReLU. This was our second hidden layer. Now if you want, you can add as many hidden layers as you want, but now I will add the output layer here. 2 hidden layers are enough. So output layer will say keras.layers.dense. Dense basically means that we want every neuron from every layer to be connected with every other neuron. We don't want any neurons in our artificial neural network that aren't connected to each other. We want a fully connected network, and hence we have said that it's a dense layer. Now in our output layer, when we are performing binary classification task, we will have just one neuron. That is when we are performing binary classification, our output will either be 1 or 0. And hence we will have just one neuron that will give us either of the output. So the output layer will consist of only one neuron, and the activation function here, as we are performing binary classification, the activation function here is sigmoid. So sigmoid. So this was our output layer, and now we have built our model. The next step is to compile it. So we will say model dot compile, and here we will say optimizer is equal to Adam. That's the currently best optimizer available for any ANN task. Next is loss. Now as we are performing binary classification, the loss function that we are going to use here is binary cross entropy. Fine. After binary cross entropy, here we have to say matrix. That is on the basis of which we have to evaluate our model. So we have to evaluate our model on the basis of accuracy. So this was the code for compile. After compiling that, now we will fit our model. So model dot fit. Here we have to provide the training set, that is xtrain and ytrain. Then the epochs. Again, the choice of number of epochs depends completely upon you. Always start with less number of epochs, and then depending upon the accuracy and loss value, you can increase the number. So we'll start with 10 epochs here, and the batch size 200. You can again give batch size if you want some different. Let's run that. Now it will take some time to run all the 10 epochs here. Until that time it's running, we will just write the code for evaluation here. So the next task, that is the 9th task here, is model evaluation. So at the last epoch, you can see the accuracy is 99% and the loss is just very minimal. Now this accuracy of 99% is on our training set. We are going to evaluate our model now on the testing set. So we will say loss comma accuracy is equal to model dot evaluate. Here we will provide our testing set, that is x test and y test. Then here we will print the model's accuracy. We will say model accuracy, and here we will say accuracy. And as we want to display our accuracy in the percentage format, hence we will multiply it by 100. Let's run that. And as you can see, we are getting an accuracy of 99% for this particular model. After that, if you want to check the information about your model, you can just say model.summary here. So it will show you what kind of model you have used. You have used a sequential model, how many dense layers you have added, the input layer, output layer, neurons here, and everything about the model. It will just display it here when you make the use of summary method. Now after that, after evaluating the model, you have to make some predictions, because to display the confusion matrix and classification report, we require the predictions first. So the 10th task that we will say here is to make predictions. And we will say model dot predict the values for x test. Let's run that. And these are all the predicted values for all the instances. We are going to save this, we are going to store this predicted values in a variable pred. So this pred will hold all our predicted values. Now when you take the look at your pred values, let's say pred, the first 5 predicted values, you can see the values are in some point decimal format and not in the main boolean format, that is 0 and 1. This is because when you make the use of sigmoid activation function in your output layer, it basically gives you the probability of the instance, that is the if the value is closer to 1, that is 0.8, 0.9, then the fraud can happen. And if it's very close to 0, that is 0.1, 0.2, that is basically 0.5 is your threshold. If the value is greater than 0.5, then it falls in the category 1, and if it is less than 0.5, then it falls in the category of 0. So 0.5 is your default threshold. If you want, you can change that. Now hence we have to convert these probabilities into the zeros and ones. So to do so, we will create another variable here of binary pred. So let me say here binary underscore pred, and here I will say pred greater than 0.5. that is if the value is greater than 0.5, that is the value of pred. If it is greater than 0.5, then it will be included in the category 1 of fraud, and if it is less than 0, then it will be included in the category of 0, that is not fraud. Let's run that and let us display the first 5 instances of binary pred. As you can see, right now they are in the form of true and false. This is because we have to explicitly convert the data type here. We will say as type int. Let's run that again. And now you can see the values are in the form of zeros and ones. So this is what you have to do. You can even change the threshold here if you want, but the default threshold is always 0.5. if you want, you can make the comparisons. So these are the predicted values, and you can compare it with the true labels which are stored in y-test here. So the first 5 true labels are this. So when you make the comparison here, the first is 0, and here even it is 0, 1, 1, then 0, 0. So the values are, the predicted values and the original values are very similar here. Now we can display the confusion matrix and classification report here. So we will say from sklearn dot model selection. So we will say from sklearn dot metrics, we will import the classification report and the confusion matrix. Now we will print our classification report. So let me say here classification report, and here we have to pass the true labels which are stored in y-test and the predicted values which are stored in binary pred. Let's run that. And this is our classification report. As you can see, 99% F1 score for both the categories and 99% accuracy. Even the precision is good, recall is good. Now one thing I would like to tell you is, we have handled the imbalanced dataset, and hence the values of F1 score for both the categories are equal. If we wouldn't have handled that, if we wouldn't have handled the imbalanced dataset and we would have worked upon that, then here the F1 score of both the categories would have been drastically different. Like it might be a difference of huge numbers, but the drastic difference between F1 score of the various categories refers to a bad model, and hence it's necessary to handle the imbalanced dataset. As we handle that, now we can see the F1 score for both the categories is equal here. So this was our classification report. Next we will display the confusion matrix, and to display the confusion matrix we will first require here import C1 library. Then we will see a variable CF which will hold our confusion matrix. Here again we have to pass the true labels which are stored in y-test and the predicted labels which are stored in binary pred. Then normalize is equal to true. Actually it's in quotes. Then we are going to display the confusion matrix using the C1 heat map. So I will say SNS dot heat map. I will pass that CF variable here. Then I will say A0 is equal to true in order to display the values on the grid of heat map. And then the theme of heat map. So I will say here, you can choose any theme you want. So I will say let's run that. And as you can see, this is the heat map. The x-axis hold all the predicted values and the y-axis hold all the actual values. So if you want to add the labels here, you can just say import matplotlib.pyplot as plt, and here you can say plt.xlabel, that is the label for x-axis, and x-axis displays all the predicted values, so predictions, and plt.ylabel, that is the label for y-axis, it holds all the actual values, so actual. Let's run that. And as you can see, this is the confusion matrix. X-axis displays the predicted values and y-axis displays the actual values. So when you take the look at your diagonal, as you can see, the first block of coordinate 0, 0, that is 0 on x-axis and 0 on y-axis as well, it displays 1, that is 100%. So every time it's doing correct classification for category 0. And when you take the look at the coordinate 1, 1, that is 1 on x-axis and 1 on y-axis, it's showing you 0.99, that is 99%. That is 99% times the original category is 1, and the model is also predicting it to be 1. Just 1% time it's happening that the original category is 1, but the model is predicting it to be 0. This is how you can just interpret your confusion matrix. I have also made the video about interpreting confusion matrix. So if you want that, I will link it in the description box. So that was the project for credit card fraud detection using artificial neural network. With an, we have built that with an accuracy of 99%. That's it for the video. Thanks for watching.